Hi everyone, this is Dr. Nak. Today we're going to be learning about power functions and polynomial functions. So let's first go with the definition. It says a polynomial function is a function of the form f of x equals a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus yada 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 plus a sub 1 times x plus a sub 0, where a sub n minus 1 all the way up to a sub 0 are constants called the coefficients of the polynomial. N must be greater or equal to 0 is an integer, and x is going to be the variable. Now, if a sub n does not equal to 0, which is this a sub n right here, it is called a leading coefficient, and n is the degree of the polynomial. Now, please note that the domain of polynomial function is the set of all real numbers. Now, as an interval notation, we'll write that as open parentheses, negative infinity, comma, to infinity, open parentheses. Now, before I go on, I just wanted to let you all know that this section is pretty heavy. We're going to be learning about a lot of things about the behavior of the graph of the polynomial functions and power functions. Before we go over any examples, let's try to understand all of the definitions. So suppose you're given a polynomial of degree n in general form. Now, if a sub n does not equal to 0, then our a sub n is called a leading coefficient. And if a sub 0 does not equal to 0, then this is called the constant term. So basically, constant term is just a number, and it does not have any x attached on it. Now, if all of the coefficients are 0, the polynomial is called the zero polynomial, which has no degree. Which means that if you're given f of x equals to 0, so this is called the zero polynomial, and the degree of the zero polynomial is going to be 0. We also say that the polynomial is written in standard form, which means that everything is laid out in descending order. So the first degree is the biggest, and the last one should be the smallest of degree. So for an example, right? So if I had something like f of x equals maybe 2x cubed plus x minus 1, then this is in fact in standard form, because look at the degree of the polynomial. The first term is degree 3. The second term is degree 1, because remember there is a missing 1 sitting here. And the last one is just a constant term. Now, the constant term, we say that the degree of the constant term is 0. So if I just look at this as just one term, 1 has the degree 0, and if I just look at this term right here, just the x term, remember x is same thing as x to the first, so this term is of degree 1, and the last one here is of degree 3. Now, all together, the degree of f is 3, because 3 is the highest exponent of the function. Anyways, so this is in standard form, so I'm going to put in standard form. Now, what is not in standard form? So let's take a look at this guy right here. G of x equals x plus 2x to the third minus 1. Notice that the degree 1 appears first, then degree 3, but degree 3 is bigger. So in this case, this is not in standard form. Let's do some examples. Example 1, determine which of the following are polynomial. So let's take a look at A. We have p of x equals 5x to the third minus 1/3 x plus 10. So what do you think? Well, I say that this is a polynomial. In fact, this is a polynomial of degree 3 already written in standard form. And also, in order to be a polynomial, all the exponents on the variable has to be greater or equal to 0, and furthermore, it cannot be a fraction. So if the exponent here, instead of a 3, if it's -3, then no, it is no longer a polynomial. And then also, instead of 3, suppose I had an exponent of 1/3. That means that our p of x is no longer a polynomial. But anyways, in this case, we're safe. This is actually a polynomial of degree 3. And furthermore, it's in standard form. All right, now let's take a look at the next one. F of x equals x plus 2 minus 3x to the 4th. Okay, so first of all, is this a polynomial? I say yes, because look at all the exponents on the variable, right? We have a 4, and then we have a 1. By the way, the constant term has a degree 0. But anyways, this is a polynomial. In this case, this one's degree 4. But is this in standard form? Nope, because in order to be a standard form, it has to start from the highest degree to the lowest in order. So this is not in standard form. So far, so good. All right, now let's look at the next one. Example, part C. G of x equals 3x to the 4th plus x minus 5 square root of x. So, what do you think? I say this is not a polynomial because of the square root of x. Now, note that, remember, the square root of x is same thing as x to the 1/2 power. Now, in order to be a polynomial, you cannot have a fractional exponent. So with that said, this is not a polynomial. All right, now let's look at something a little bit more different, part D. H of x equals x squared plus x minus 1 divided by x cubed minus 1. Now, all right, so is this a polynomial or not? Well, if I look at them separately, right, denominator versus the numerator, numerator is a polynomial of degree 2 in standard form. And then also the bottom is also a polynomial of degree 3 in standard form. However, if you have a fraction over the polynomial over another polynomial, this is no longer a polynomial. In fact, this is called the rational function, which we're going to be learning about in maybe next section. So let me just write that. Yes, this is the polynomial, and then also this is a polynomial, but all together, this cannot be a polynomial. All right, in fact, this is called the rational function. So here's our answer. Let's look at the next one. G of x equals to 8. Is this a polynomial? What do you think? I know this one's a little bit weird because we don't have that variable. However, it is in fact a polynomial because remember that constant term was denoted by a sub 0. So here it is. This is nothing but a constant. So in fact, yes, this is a polynomial of degree 0. So if the function equals the constant, it is always going to be a polynomial of degree 0. All right, so maybe let's just look at the one more. Part F, h of x equals negative 2x cubed times the quantity x minus 1. What do you think? I say that it is a polynomial because, look at it, if I distribute the negative 2x to the third to each term, and what do we get? We're going to have negative 2x to the fourth and then plus 2x to the third. Okay, so look at it. Isn't this nothing but a polynomial of degree 4? In fact, it's written in standard form. So yes, this is a polynomial of degree is 4, and this is in standard form. Okay, so let's just summarize this. So we have a degree and a form, name, and what the graph is going to look like. So if we're talking about the no degree, you better have a zero polynomial. So the form will be f of x equals to 0. Now, what do we call that? Zero function. Now, if you graph it out, it's going to be the x-axis, because remember, f of y equals f of x, right? So this is telling you y equals to 0, which is nothing but the x-axis. So here's the graph for that. Now let's go with the degree 0. Please note that degree 0 is different from no degree. But anyways, degree 0 is always going to look like f of x equals a constant. But the constant cannot be 0, because if so, then we're going to have a no degree polynomial, which is a 0 polynomial. But anyways, what is the name for that? We call that the constant function. Now, what does the graph look like? It's always going to be the horizontal line with the y-intercept a sub 0. So if it's a constant function, you're going to have a graph that's looking like this. Now, in fact, this will be f of x equals, the y-intercept is 2, so f of x equals to 2. Now, let's go with the degree 1. What does it look like? Well, our f of x is going to look like a sub 1x plus a sub 0, where I forgot to mention that a sub 1 cannot be 0. Now, what is that called? We call that a linear function. Do you all remember mx plus b? When you graph f of x equals mx plus b, that was nothing but a linear function. But anyways, what are we going to get? Non-vertical, non-horizontal line with the slope a sub 1 and then the y-intercept of a sub 0. So here will be an example. F of x equals 1/2 x minus 1. So notice that our y-intercept is at -1. From there, you're going to have to rise 1 and then run 2 units to the right. So you're going to have 1 over 2 as a slope, and then the y-intercept of -1. Now let's go with the degrees 2. So what does it look like? We have f of x equals a sub 2x squared plus a sub 1x plus a sub 0. And please note that a sub 2 cannot be 0. Now, what's the name for that? That's called a quadratic function. And what does the graph look like? It's nothing but a parabola. Now, if the leading coefficient, which is x sub 2, is positive, then your parabola is going to open upward. And if your leading coefficient is negative, it's going to open downward. So here's just a very simple example of the quadratic function, which is f of x equals x squared. Now, it's opening upward because the leading coefficient, which is the constant term that's stuck on the x squared, is 1, positive 1. That is the reason why it's opening upward. All right, now let's talk about the power function. So let's go with the definition. It says a power function of degree n is a monomial function of the form f of x equals a times x to the n, where a is a real number, a cannot be 0, and n greater than 0 is an integer. So monomial is nothing but a polynomial with one term. And binomial, I'm sure you've heard that before. Binomial is same thing. It's a polynomial with 2 terms. And trinomial. Trinomial is a polynomial with 3 terms. So some of the examples of power functions are, like maybe we can call it f of x equals 3x. Now that's a polynomial of degree 1, but it only has 1 term. So it's a monomial of degree 1. So this is a power function. And then we can also say like maybe g of x to be -5x squared. Notice that that's a monomial of degree 2, so which is same thing as the power function of degree 2. And then maybe we can go h of x equals to 8x cubed. So again, this is a monomial of degree 3. So yes, this is a power function of degree 3, and so forth. Now let's talk about the behavior of the graphs of power function. Now, your degree can be either even or odd. So first, let's take a look at when the degree is even on the power function. So here are 3 graphs of power function. I took the leading coefficient a to be 1. So we're looking at y equals x squared. We've seen this guy many, many times. And then the blue one is y equals x to the 4th. and the green one is y equals x to the 8. So in your own words, what's going on as n increases when n is even? Well, here's our y equals x squared, right? Now let's just look at y equals x to the 4th. Doesn't it look like it's getting skinnier at the top, but it flattens towards the bottom? And then let's look at x to the 8th, same thing, right? It's getting skinnier, but it's getting more flat at the very bottom. Now, how the graph looks, it almost looks like, you know, the green curve, which is y equals x to the 8th, and then also y equals x to the 4th. They look like they're hovering over all the x-axis, right? It's touching the x-axis, but in fact, it is not. So if you have a power function x to the n, if n is even, they're only going to touch at only one point, which is at the origin, 0, 0. Also, please note that, do you see the common intersection point? That will be at when x is 1, y is 1, and then also when x is -1, and then y equals to 1. So for a summary, let's think about it. Okay, so if f is an even function, so its graph better be symmetric with respect to the y-axis. It is symmetric, it makes sense. And then the domain is set of all real numbers, and the range is the set of all non-negative real numbers, because remember, domain is set of all x values, and the range is all the set of y values. Now y is going to start from 0 all the way up to infinity. All right, and the graph is always going to contain the points -1, 1, 0, 0, and then 1, 1. And finally, as the exponent n increases in magnitude, the graph is steeper when x is strictly less than -1, and then, or x is greater than 1. But for all x near the origin, the graph tends to flatten out and lie closer to the x-axis. So here's the summary of properties of power functions. F of x equals x to the n. N is positive and also at the same time an even number, or integers I should say. So number 1, property 1, f of x is an even function, which implies that the graph must be symmetric with respect to the y-axis. And domain of f of x is set of all real numbers, and the range of f of x is from close bracket 0 all the way up to infinity. Now, the third one is this: as n gets bigger, the graph is steeper when x is strictly less than -1 or x is greater than 1. But for x near the origin, the graph flattens out and lie closer to the x-axis. And again, here are the graphs that we talked about earlier. Now let's talk about the properties of power function when n is positive odd integers. So here are the graphs of y equals x cubed. That's this black one right here. And then y equals x to the 5th. That is the red curve here. And then y equals x to the 7th. That is the blue graph. So what do you notice? Well, I notice first that the graph is symmetric with respect to the origin, of course, because f of x is an odd function. That's one of the properties of the odd function. And the domain and the range, let's talk about that. Looks like domain is set of all real numbers. And what about the range? Looks like range is also all real numbers. Now the graph always contains the point 0, 0, and then also -1, -1, which is this intersection here. Hopefully you can see that. And then 1, 1. So let me just write it, 0, 0, -1, -1, and then this point is 1, 1. And again, although the graph looks like it's touching the whole entire x-axis in this interval here, but it is not. The only point of intersection is at 0, 0. Also, what else? When x is less than -1, right? Notice that the graph with the bigger exponents gets steeper. And then same thing here, when x is greater than 1, which I'm looking at from this point on, notice that as the exponent increases, look at the blue graph, that gets steeper than the y equals x cubed or y equals x to the fifth. And also towards the origin, right? Let me see. The higher the exponent, it flattens out around the x equals to 0. So let's write down the summary. Properties of power function f of x equals x to the n is a positive odd integer. Number 1, f of x is an odd function, which implies that the graph is symmetric with respect to the origin. Domain of f of x is all real numbers, so is range of f. So range of f of x is also all real numbers. Now, as the n gets bigger, the graph is steeper when x is strictly less than -1 or x is greater than 1. But for x near the origin, graph flattens out and lie closer to the x-axis. Let's do some examples. Example 2, graph f of x equals 1 minus x to the fifth. Now, what we're going to do is we're going to use the transformation of the graphs to graph 1 minus x to the fifth. All right, we got this. So let's do this. So first, let's graph y equals x to the fifth. So let me just go with first function is x to the fifth. Now, we know that since the exponent is odd of this power function, the key points are 0, 0, and then 1, 1, and then -1, -1. Those are the key points that our graph has to go through. So let's just give a rough sketch. Oh no. Okay, pretend that's not so bad. So this is our function y1 equals x to the fifth. Now the next graph that I'm going to graph is, let's just call it y2, is negative x to the fifth. Now, do you remember what we need to do? You're right, multiply by -1, which is the same thing as reflect y1 about the x-axis. Okay, I'm going to write that out. So I'm going to say reflect y1 about the x-axis. All right, so instead of -1, -1, we're going to have -1, 1. Oh, that will be right here. And instead of 1, 1, what we're going to get is 1, -1. Oh, I'm just going to go over here. Oops. So this point is 1, -1. I hope you can see that. And then again, it has to go through the origin. All right. So this is the best I can do. So y2 is negative x to the fifth. All right. So one more step. Our final graph. Do you see that I can rewrite this as negative x to the fifth and then plus 1? That's exactly the same thing. So what we need to do is we need to take y2 and shift 1 unit upward. So let me just write the final graph as y3. So this is going to be 1 minus x to the fifth, or same thing as negative x to the fifth plus 1. So what I'm going to do is I'm going to take all of the key points and then shift 1 unit above. So if I do that, let's take a look at this point right here, -1, 1. So I need to shift 1 unit upward, so I need to make a dot here. Now this point here is -1, what is that? -1, 2. Let me just write it over here, -1, 2. All right, and then let's shift the origin 1 unit above, so that will be here. So what is that? When x is 0 and then y is 1. So I'm running out of room here, so let me just write it here. So I'm going to write here as 0, 1, and then this point right here is -1, 2, and then the last point 1, -1, if I shift that point 1 unit, will be right here. So this is 1, 0. Okay, so let's graph this out. This is the best I can do. Okay, so that's the final graph is our y sub 3, which is 1 minus x to the fifth. So this is the actual graph, kind of exaggerated a little bit. So what do you think? We did pretty good. Yeah, I think we did pretty darn good. Our next topic is real zeros of a polynomial function and their multiplicity. Let's take a look at this graph. So this is the graph of a polynomial because it is continuous, it's smooth, and there's no sharp corners or point of discontinuity. But anyways, this graph also has 4 x-intercepts. X-intercepts are where the graph is going to touch or crosses the x-axis. Now, if you have 2 continuous x-intercepts, right? So for example, this is the first intercept, this is the second x-intercept. Notice that your graph is either going to dip down the x-axis or in this case, goes above the x-axis. So first, our goal is this. Given the function, how are we going to find these x-intercepts? Now, the x-intercepts are called the zeros of the polynomial function as well. Now remember that at x-intercept, your y value is always going to be 0. So basically what you're computing is f of x equals to 0, and then you just solve for x, meaning set y equals to 0 and then you solve for x. Now the real zeros of the polynomial function is exactly the same. It basically turns into an x-intercept. But anyways, let's just write down the formal definition. It says that if f is a function and r is a real number for which f of r equals to 0, then r is called a real zero of f, or the x-intercept. Now, it's easy for us to find the x-intercept or the real zero of f if your function was written in terms of something of the form, I don't know, f of x equals x minus 1 squared, multiplying here by x plus 4. Because remember, to find the x-intercept, all you have to do is set y equals to 0 and then you solve for x, right? So to find the x-intercept, which is same thing as the real zero, all you have to do is set y equals to 0 and then you just solve for x. So if the polynomial is written in factored form, such as in this case, let me just write this out. This is in factored form. All you have to do is to set y equals to 0. So basically what you're going to do is you're going to set x minus 1 squared times x plus 4 equals to 0. And then all you got to do is solve for x. Well, so that implies that I'm going to apply this zero product property. So you're gonna set x minus 1 squared is 0, or x plus 4 equals to 0. So that implies that x minus 1 equals to 0. So x equals to 1 is an x-intercept, or the real zero of f. And then also x equals to negative 4, so is also an x-intercept, or the real zero of our function f of x. So it's much easier if you're given the factored form to find the zero of the polynomial. And let's just view this in a different way as well. So notice that the real zero of f is x equals to 1. So that means what then? X minus 1 must be a factor of f of x. Same thing here. If negative 4 is the zero of f of x, then x minus minus 4, which makes it into a x plus 4, must be the factors of f of x. So keep those in mind, and let me just try to write down the summary of all the equivalent statement with r being the real zero of a polynomial function. So let's write down the equivalent statement as r is a real zero of the polynomial function f. Well, that's same thing as saying r is an x-intercept of the graph of f. And also we just talked about x minus r must be the factor of f. And the fourth one is this. R is nothing but the solution of the equation f of x equals to 0, right? Because, let me see, R is a solution to the equation f of x equals to 0. Basically set y equals to 0 and solve for x, and then let's just call that x value to be r. Remember, r is some numerical value. So all these four statements are equivalent. Let's take a look at this example. Example 3, find a polynomial function of degree 3 whose zeros are -3, 2, and 5. Okay, so let's first go back to statement number 3, right? If -3 is a zero of f, then x minus r, so you're going to have x minus -3 is a factor of f. So if the zeros are -3, 2, and a 5, then we know that, let me just write it out like this. So we know that x minus -3, which is same thing as x plus 3, and x minus 2, and x minus 5. Now, they're all must be a factors of f of x. So what we can do is we can write f of x as x plus 3, and then x minus 2, and then x minus 5. Now, I left the leading coefficient here to be 1, but remember, I'm just asking you to come up with a polynomial function, right? So you can get fancy here and put 10 or 5 if you want to, or in general, let me just denote it as a. A is some real number. Now, let's just check to see, make sure that this is going to turn out to be degree 3. I think it does, because look, if I multiply the first term together, the biggest number that you're going to get is x squared. Not biggest number, sorry. Biggest exponent on the variable, we can get 2. And then if I multiply x squared times something of the form x minus 5, then do you see that we're going to have a third degree polynomial? So I'm just going to box that for our answer. Okay, now let's just play with this function for a little bit. What I'm going to do is I'm going to take a equals to 1, just like how we had it before. Now, if I take a equals to 1, then our f of x is just going to become x plus 3, x minus 2, and then x minus 5. So let's just multiply this out. So this is same thing as x squared, and then you're going to have minus 2x plus 3x. You're going to have a plus x minus 6, multiplying here by x minus 5. Did I do that right? I think that's right. So this is going to equal to x cubed minus 5x squared, and then plus x squared minus 5x, and then minus 6x, and then plus 30. Now combining the like term, what the heck do we get? X cubed, and then you're going to have minus 4x squared. Is that right? And then you're going to have minus 11x, and then the constant term is 30. So let's look at that. So f of x is exactly equal to that third degree polynomial if we take a equals to positive 1. Now here is our actual graph of our function f of x. So do we have the correct x-intercept? Let's see. We have an x-intercept, let's just call it a real 0 just to be fancy now, at this point here, and then here, and then at this point here. So I believe that this is when x equals to 5, y is 0, and then this point is when x is 2, y is 0, and then this point here is, what is that, -3, 0, so it does make sense. Now, I also want you to notice this because we're going to have to talk about this anyways. Notice that this function is what? Degree 3, right? So look at it. How many bumps do we have? How many max and mins do we have? Well, here's one, and then it's going to churn down, and then it's going to churn back upwards, right? So here we're going to have 2 churning of the graphs here. So this is a first churning, and this is going to be the second churning. Now, if the degree of the polynomial is 3, the number of times that the graph is going to churn is 1 less. So in this case, since this is degree 3, that means that your graph better have, or I should say better churn at 2 different places. Also, we took our a to be positive 1, right? So let's just look at the behavior of the graph. So basically, you're going to start from down below, and then down below, and then you're going to go up, down, and then up. So your graph is going to be facing this way. Now, what do you think if the instead of a equals to 1, if I have a equals to -1? What do you think? We learned that, right? That's nothing but a reflection about the x-axis, isn't it? So instead of the graph is going from down, up, we're going to have a different one now. So we're going to start out with the up, and then down, up, and then down. So this is if a is negative. But you know what? We're going to learn all about that later on. Now, what do you think it's going to happen if I take, instead of a equals to 1, if I take a equals to 2? Do you think we're still going to have the same zeros? Well, answer is yes, because if this is 2, then how do you find the zeros? You just basically set this whole equation equal to 0, so your zeros are still going to be -3, 2, and a 5. Now, before we start having a lot of fun with graphing for this section, we have to know this definition here. So let's just go over it. So definition, if x minus r to the m is a factor of a polynomial f, and x minus r to the m plus 1 is not a factor of f, then r is called a zero of multiplicity m of f. You're probably going, what the heck is this? Like with the m and then the whole m plus 1? It basically is telling you is this. So let me just do it by the example. So for the polynomial f of x equals 5x squared times x plus 4 times x minus 1/3 to the 4th power. So let's find first of all, let's find the zeros, and then let's count the multiplicity. So the zeros are, can you tell me what the zeros are? So basically, you're going to have to set this whole thing equal to 0, and then you solve for x. So that means that you're going to have to set each term equal to 0. So if I have to do it step by step, so this means 5x squared is 0, x plus 4 is 0, and then x minus 1/3 to the 4th has to be 0. So that implies that our x squared is going to be 0 over 5, which is 0. So that implies that our x is 0. All right, and then this one's easy. So this is x is -4, so that's going to be the 0 of f. And then this one is okay too, because this implies that you're going to have x minus 1/3, taking the 4th root on both sides. 4th root of 0 is just 0, so our x is just going to be 1/3. So these are the zeros of our given function f. All right, now let's go with the multiplicity for each of the zeros, right? So the multiplicity means this. How many times is our zeros going to repeat? Well, since, look at it, this x equals to 0 came from 5x squared, right? So that means that your 0 is going to repeat twice. So we say that 0 is a 0 of f with multiplicity of 2. And for x equals to -4, well, let's look at it. That came from x plus 4 to the, this is the first power, right? So it's only repeat once. So that means that -4 is a 0 of f with multiplicity of 1. And right here, x equals to 1/3. Now, that has a multiplicity of 4 because it came from this polynomial x minus 1/3 to the 4th power. So this 0 repeats 4 times. So we say that the multiplicity of 1/3 is 4. I'm going to write that out. So here it is. Again, 0 is a 0 of f with the multiplicity of 2 because it repeats twice. And -4 is a 0 of f with multiplicity 1 because there's a hidden exponent 1 sitting here. And then 1/3 is a 0 of f with the multiplicity of 4. So that's pretty much what this definition is telling you. Anyways, let me just box that for the answer. And let's move on. Let's take a look at this graph that we drew earlier. Okay, so we talked about that 2 consecutive zeros. Your graph is either going to be above the x-axis or the below the x-axis, right? Because here's the 2 consecutive. In this case, it's above the x-axis. That means the y value is positive. And then here are another 2 consecutive zeros, or the x-intercept. In this case, our graph dips down the x-axis. That means that your y values are going to be negative. And then another consecutive zeros. So in this case, it touches the x-axis and then dips down and then crosses. But either in any case, our y value here is going to be negative as well. So keep that in mind, and let's take a look at the next example. Example 5, consider the polynomial function f of x equals x plus 1 squared times x minus 2. Part A, let's find the x and the y-intercepts of f. So let's first go with the x-intercept. X-intercept is same thing as the 0 of f. Now how do you do that is you set y equals to 0 and then you just basically solve for x. That's how to find your x-intercept. So here what we're going to do is we're going to set 0 equals x plus 1 squared and then x minus 2. So that means that either x plus 1 squared is going to go to 0. Here I'll just write everything out. Or x minus 2 is going to go to 0. So this implies that taking the square root on both sides, square root of 0 is a 0. So this is what we're going to get. So here you're going to have x equals to negative 1 is the 0 of our f of x. And then another one is going to be x equals to 2 is the other 0, or the x-intercept. So therefore, our x-intercepts are x equals to negative 1 and x equals to 2. So let me just box that for the answer. And let's go with the y-intercept. So how do you find the y-intercept is you basically set x equals to 0 and then you just solve for y. So if I do that, then we're going to have y equals 0 plus 1 squared times it by 0 minus 2. So this is same thing as 1 squared, which is 1, times the negative 2. So this is going to be negative 2. So therefore, we're going to have the y-intercept is at y equals to negative 2. So let me just box that for the answer for part A. And although I didn't ask you this, let's count the multiplicity of 0 when 0 is negative 1. So what's the multiplicity? Well, it came from x plus 1 squared. So this one has a multiplicity of 2. And then what about 2? Well, 2 came from x minus 2 to the first power. You're setting that equal to 0. So here we're going to have a multiplicity of 1. Now part B. Use the x-intercepts to find the intervals on which the graph of f is above the x-axis and intervals on which f is below the x-axis. So let's just think about this. Let's just give a little rough sketch, okay, just so that you kind of understand what's going on here. So let me just jot down the y-intercept. I guess y-intercept is not all that important at this point, but I'm just going to do it anyway. So here's y-intercept of negative 2, and x is negative 1 was a 0, and then x equals to 2 was another 0, right? So again, when we talked about is this, in between the 2 consecutive zeros, your function can either it's going to go above the x-axis or below the x-axis. So what we want to do is this, what's going to happen between negative 1 and 2? Is my graph going to go above the x-axis, or is it going to go below the x-axis? Now suppose you want to above the x-axis, right? Then what's going to happen from negative infinity to negative 1? What about this tail end of the graph? And then same thing here. At 2 to infinity, what's going to happen to my graph? Is my graph going to go this way, or is my graph going to go this way? So that's what we're trying to find out. So to find that, I like to make a little chart. So let me just draw a chart like this. All right, so here's my chart. So basically what I did was I just drew the number line from negative infinity to infinity, and then I just put our zeros here in order. Now I broke this down into 1, 2, 3, 4, 5 different categories, which is the interval, test point, value of f, above or below the x-axis, point on the graph. Okay, so basically the interval that we're talking about is this. So let's just go back to this picture, right? So from negative infinity to our first 0, is my function's gonna be above the x-axis or below? Where is it gonna be? So here I'm going to chop that up into 1, 2, 3 different intervals. One of them is from negative infinity to negative 1. And then next one is negative 1 to 2. And the last one is 2 to positive infinity. Okay, so again, negative infinity to negative 1 will tell us what's going to happen to our graph from on this interval. Negative 1 to negative 1 to 2, we're going to determine whether the graph is going to go above or below the x-axis in this interval. And then same thing from 2 to infinity. All right, now test point. Test point is this. You're going to have to pick any number between negative infinity to negative 1, and what we're going to do is we're going to plug that value back into our f of x. Now, remember, this is y equals f of x, right? So if I plug some test point in to f of x and suppose that the result is positive, that's same thing as saying y is positive. Now, where is our y positive? That's above the x-axis. All right, and then we're going to do the same thing for each of the interval. All right, and then we're going to go with the value of f. So meaning, all right, if I'm going to pick the test point, now what is the corresponding y value at that test point? And then this, we just went over it. Is it going to be above or below the x-axis or not? And then point on the graph. Basically what you need to do is you just translate value of f and then make that into an ordered pair. You're like, what? So let's just do it together, okay? So we got our intervals going on. We have 3 different intervals now. Now let's get the test point. So you can pick any number between negative infinity to negative 1. So what I'm going to do is, you can pick whatever you want, but I'm going to take negative 2. Negative 2 is definitely in there, right? So now let me compute f of negative 2. Okay, now if I plugged it in negative 2 in place of x, do you see what I'm doing here? So let me just do it as a side work. I don't know if I have enough room for this. So I have f of negative 2. So this is going to be negative 2 plus 1 squared. So you're going to have negative 1 squared times it by negative 4. So this is going to be negative 1 whole quantity squared is positive 1. So you're going to have a negative 4. So this is going to be negative 4. So basically it's telling you is this. If I plugged it in x equals to negative 2, which is over here, our y value is negative. So that means that our graph from negative infinity to negative 1 has to lie below the x-axis. All right, so that's what the next column is asking you to do. Above or below? Well, this one's going to be below because y value was negative 4, which is negative. Now, point on the graph, right? At the test point is when x is negative 2 and then y is negative 4. All right, so far so good. Now, we're going to be doing the same thing for each of the interval. So let's take a look at the next interval, right? So that will be from negative 1 to 2. You can pick any number that you want in between. So how about, you can pick 1. How about a 0? 0 is inside of here, isn't it? So I'm going to pick 0. And next, value of f at the test point is f of 0. Now, if I plugged it in, 0 in place of x, then here you're going to have 1 squared. 0 plus 1 squared is 1 squared. and then multiplying here by negative 2. So here I believe that, let me just double check. So let's go with f of 0. So you're gonna have 1 squared multiplying here by negative 2. So it looks like we're gonna have a negative 2. So what's gonna happen? It's going to be dipping below the x-axis again. All right, so what we just found out is this: our graph, whatever it is, from negative infinity to negative 1, it's gonna be below the x-axis. And then also, can you tell what I'm trying to draw here? And then from negative 1 to 2, this graph also has to be below the x-axis. So what's going on here? Sorry, this is really hard to see. I'll redo it again on the next page. But so it has to be negative, right? So if I cut across it, then do you see that from negative 1 to 2, I'm going to assume some positive values, right? So that cannot happen. So what's your only option? So that between negative 1 to 2, your function is below the x-axis. Well, it's going to have to touch x equals to negative 1 and then dip down below. So this will be your only option that you have going on right now. But anyways, let's go with the point on the graph. So this is going to be 0, negative 2. So it does go through the y-intercept. I just got lucky. I just drew the curve and it happened to lie on the y equals to negative 2. Now let's go with 2 to infinity. Okay, so you can pick any number. I'm going to pick 3. Now I'm going to compute f of 3. So f of 3 is 4 squared multiplying here by 3 minus 2 is 1. So this is going to be 16. Oh, look, now we finally have a positive. So that means that, oops, not positive. It's going to go above the x-axis. All right, so let's just look at it, this little rough sketch here, right? So it's going to go up, touches at x equals to negative 1, dips down below, and it's going to go through the y-intercept. And then this has to be negative here, right? Now from 2 to infinity, it is going to be above the x-axis. So do you see that there is no way that this graph is going to dip down immediately at x equals to 2? It has no choice but to cut across the x-axis. So this is my little rough sketch of the graph. But anyways, here our point is going to be 3, 16. All right, so I'm going to try to write this out nicely and work it on the bigger space on the next page. So here is the same chart that we just drew on the previous page. Now let's translate this out. So let's graph this nicely now. All right, so let's first jot down our zeros. So let's just recall that our function f of x, I just rewrote it at the top, was x plus 1 squared times x minus 2. So that means that we got a 0 of negative 1 with the multiplicity of 2, and then 0 of 2 with the multiplicity of 1. All right, so let's keep that in mind, and let's just jot down our zeros. So what do we got? We got negative 1, and then 2. And then our y-intercept was negative 2, wasn't it? Okay, so now let's draw this out. So from negative infinity to negative 1, so from on this region here all the way up to negative 1, it's going to dip down below the x-axis, right? And then for the next interval here from negative 1 to 2, right, it also has to be below. So that means that there is no way that this graph can cut across the 0, because if it does, that means what then? From negative 1 to 2, your graph is going to go above the x-axis, but that's not true because we computed it, it's going to be below. So only choice that we're going to have is this. Your graph is going to go up, and touches the 0, and then just touches it, not cross it, and then it's going to have to dip down and then crosses that y-intercept and then come up. But anyways, let me just jot down the point on the graph. So I'm looking at these guys now. Let's just plot these points. Okay, so we're going to have -2, -4. And then 0, -2, that's just our y-intercept. And then, 3, 16. Oh no, it's probably like way up here somewhere. Anyways, let's sketch it out. So for sure, we're gonna have from -infinity to -1, it's gonna be below the x-axis, and then it has to touch and then come back down and then go through the y-intercept. Now the question is this, right? From -1 to 2, so in this region, I know that our function has to go below the x-axis, but the thing is, how far below is it gonna go? You know, is it gonna just like automatically turn this way, or is this graph gonna go a little bit more downward then turn? So just to be on the safe side, right, let's compute where this graph is gonna go at x equals to 1. All right, so when x equals to 1, let me just write it somewhere. Where can I write it? Okay, so when x equals to 1, let's just compute f of 1. So f of 1 is going to be 1 plus 1 squared, and then you're gonna have 1 minus 2. So this is gonna be 2 squared multiplying here by -1, so you're gonna have a -4. So 1, -4, your graph is going to go through that. So let me just jot that out. So this point right here is 1, -4. So actually your graph is going to go downward a little bit. So here, let me just go like this. And then it's going to go up from here to 2. I think that makes sense, right? Our graph is still below the x-axis. Now let's go with from 2 to infinity. All right, so in that case, I know for sure that it's gonna have to lie above the x-axis, right? So that means that I cannot dip down. I have to keep going up and up and up, and I'm going to reach 3, 16. All right, so let me just draw that out. So I'm gonna go keep going up and up and up and up. Oh no, this is good enough. All right, this is good. All right, so our graph is going to look something like this. Wasn't that a little fun? I really enjoyed it. Yeah, it's tedious and all, but look at it. You can totally graph out our f of x as long as I know the zeros. And if I could analyze just a little bit, is it going to go above the x-axis? Is it going to go below the x-axis? Right? And then just pick some test points to just determine the behavior of the graph. But anyways, let's take a look at this, right? Maybe you can't tell immediately. So when 0 at x equals to -1, we had a multiplicity of 2. So here we had an even multiplicity. So what happens? What happened? Did it cut across, or did it touch and then go down? Well, I think it touched and then went down, right? So basically it doesn't cross, it touches when the multiplicity was 2. Now let's go with this 0, which is x equals to 2. Now that one has a multiplicity of 1, which is odd, right? So when it's odd, look at it, it crosses the x-axis. Now, is that always going to be true? Answer is yes. So that's what we're going to be talking about next. Let's summarize this here. Let's first take a look at if r is a 0 of even multiplicity. Let's talk about numerically. The sign of f of x does not change from one side to the other side of r, which is same thing as what? It's going to touch the x-axis and it's going to have to dip down somehow. So that way, notice that from -infinity all the way up to this point, our sign of f of x is going to be negative, which indicates that it's going to dip down the x-axis. And then on the next one, it also has to be below the x-axis. That's what it means. The sign of f of x does not change from one side to the other side of r. So if this is r, then our sign of f of x are both negative, which indicates that it's going to go below the x-axis. And graphically, as we talked about, the graph just touches the x-axis. It's not going to go cross it. So that always happens if r is a 0 of even multiplicity. Now let's talk about if r is a 0 of odd multiplicity. We're going to do the same thing. Let's analyze numerically and graphically. Numerically, the sign of f of x changes from one side to the other side of R, which means that suppose this graph is going to be negative. Our f of x is negative, right? That means it dips down below the x-axis. Now from this 0 to the next 0, it's going to have to go above the x-axis because so that way our sign of f of x is going to change, right? So this indicates that this portion is f of x is negative, and then above it is f of x is positive. So that's what that means. Now let's go with graphically. Graphically, it means that the graph must cross the x-axis. Isn't it neat? I really enjoy this. Anyways, let's go back from example 3 that we did during this lecture. This is what we did in example 3. We came up with our f of x to be x plus 3 times x minus 2 times x minus 5, and then we multiplied it out, and then we ended up being the third degree polynomial, right? And then I asked you, how many times does the graph turn, right? Meaning, how many maximum and then minimum points do you have in one entire graph? Well, we have 2, and this is degree 3. So these points here are called the turning points, where the graph is going to increase, and then at that point, it's going to start decrease, or vice versa. Here, you're going to go decrease, and then at this point, it's going to start increasing again. So these 2 points are called the turning points. Now, there is a relationship between the degree of the polynomial and a turning point. Now, as you guessed, if it's degree 3, then we have 2 turning points. So guess what's going to happen if the degree is 4? You're right, it's going to have 3 turning points, and that's actually a theorem. So that's what we're going to talk about next. Let's go with the definition of the turning points. So it says the points at which the graph changes direction are called turning points. Each turning point yields either a local maximum or local minimum. And here is the big theorem. It says that if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. So if it's the degree 4, then the graph of f has at most 3 turning points. So it can be 3 turning points, 2 turning points, or 1, or none, which probably not going to happen quite often. The very last big thing that we're going to talk about in this section is called the end behavior of the polynomial functions. So basically it means if the function has an eventh degree, right? Degree 4, degree 2. What is the behavior of the graphs going to be? And what if our f of x is x cubed, x to the 5th, or you can be negative x cubed, negative x to the 5th. Now, where is the tail end of the graph going? So those are the things that we're going to be talking about now. Let's read this theorem together. End behavior. This is a theorem. It says for large values of x, either positive or negative, the graph of the polynomial function f of x equals a n x to the n plus a sub n minus 1 times x to the n minus 1 plus yada 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 plus a1x plus a sub 0. So this polynomial resembles the graph of the power function y equals a sub n times x to the n. So basically this is telling you is this. Suppose you're given I don't know, maybe 5x to the 3rd plus 2x squared or something like that, right? If I want to graph that out, the behavior of the graph of this whole entire polynomial is going to be resembles the form of just 5x to the 3rd. That's what this is telling you. So if I have to give a little example, right? So suppose I'm supposed to graph f of x equals, I don't know, x to the 3rd minus 3x and then minus 2. All right. Now, the theorem is telling you is this. This function f, if you have to graph it out, it's going to look kind of like just x to the 3rd. It's going to mimic the form of x cubed. So just the x cubed function is going to look something like this. It's going to go this way, something like that. All right, so this our polynomial function is going to mimic x to the third for large values of x. Now, just to show you this, please note that our blue curve is just our y equals x cubed. And then our purple one, sorry, it's in red, but our f of x is given by this graph here. All right, so notice that, look at the end behavior. End behavior meaning the tail end of the graphs. Okay, so look at it. If it's positive x cubed, right, the tail end of the graph is going upward here. That means that our function f of x, it's also gonna go towards the same direction. Now, do you see this part okay too? So this is the curve of y equals x to the third. Now look at the tail end of f of x. It's going to go towards the same direction. And that's pretty much what the theorem is saying. Now, what I wanted to do here is this. I would like to summarize what the end behavior of the graph is going to be if n is even, and then also when n is odd. If you can memorize that, your life will become so much easier when you're asked to graph a polynomial function. All right, so let's first take a look at this. So what I have here are the power functions, two power functions with the even exponent. So we have of the form f of x equals ax to the n. So in this case, our a is positive and then our n is even, because we have y equals positive x to the fourth, y equals positive x squared. So this will be the behavior of your graph of the power function. So if a is positive, n is even, the tail end of the graph is always going to go upward in this way. Now let's take a look at f of x equals ax to the n. That's a power function where a is negative and then n is even. So for examples, we have y equals negative x squared and y equals negative x to the fourth. As we learned that it's nothing but a reflection about the y-axis of y equals x squared and then y equals x to the fourth. But look at the tail end of the graph. That's called the end behavior. It's always going to go downward this way and then downward this way. Now let's talk about the end behavior of the polynomial function when n is odd. So let's take a look at the power function of the form f of x equals ax to the n. A is positive and n is odd. So here for an example, I have y equals x cubed and y equals x to the seventh. Now let's define the end behavior of the graph. So the end behavior, this tail end is always going to go up, and then this tail end is always going to go downward if a is positive and n is odd. It's almost like the disco like dancing move with the hands, but whatever. Anyways, let's look at the what if a is negative. So here are the two graphs of y equals negative x to the seventh. That's the green one, and then y equals negative x cubed. Now, if a is negative and n is odd, we're always going to end up with this behavior towards the end of the graph. So it's always going to shoot up this way and then going to shoot down this way. I just wanted to show you these because, we already know that given x to the fourth polynomial function, it's going to mimic just like the power function y equals x to the fourth and so forth. So if you know the end behavior, where the tail end of the graphs are going, then it is easier for us to kind of sketch out the graph. I mean, at least to me, it's very helpful. Anyways, how you all doing up to here? I know it is exhausting. It's so much information, but you can do it. And there's one more notations and concept that you're going to have to know for this section. And then after we understand that, then we'll graph the polynomials out by all the information that we just learned. All right, hang in there. Okay, so our next topic is limits at infinity. Now, we're going to be introducing some notations to describe mathematically, more like in a calculus way, how the tail end of the graphs are going. All right, so let's just look at this graph, right? So this is nothing but a graph of y equals x to the fourth. All right, now what we want to do is this. We want to express the tail end of our behavior by using some calculus notation, which is called the limits at infinity. Okay, so all right, so ready? Now let's try to describe the tail end of this graph. Now notice that as x is going towards negative infinity, right? Where is the tail end going? Well, the tail end is nothing but, at the y values are going to assume infinity when x approaches towards negative infinity. Do you see that part okay? So we write this as f of x, our function f of x, the tail end of the graph is going to go towards positive infinity as x travels towards negative infinity. So that's how you would describe the end behavior of this graph. All right. And let's take a look at the other tail end. Let's take a look at this one. All right. So ready? Now, that means our x is going to be traveling towards positive infinity, right? As x goes to infinity, positive infinity, where's my corresponding y value going? Well, it's going towards positive infinity, isn't it? So rewrite it as, sorry, not f of x equals infinity. I didn't mean to write that. F of x goes to infinity. Sorry about that. That's an arrow right there. So here we would write it as f of x goes to, our y value tends to go to positive infinity as x goes to positive infinity. That would describe that tail end of the graph. Now, those of you who's going to be taking calculus, there is a specific notation for that. Now, to express f of x goes to infinity as x goes to negative infinity, we write it as the limit as x goes to negative infinity of our function f of x, in this case x to the fourth. This is going to go to infinity. That's how you would write it in first semester calculus. All right, and then here it's the same thing. On this tail end on the right hand side, this tail end right here, how do I put this on a proper calculus limit notation? I can write this as the limit. Now the bottom is always going to be where x is going. Well, x is going to infinity, and then next one is your function f of x. In this case, our x to the fourth is our function. Now this is going to go towards, now you put where the f of x is going to go. So here it's going to go to infinity, and that's how you write it. Don't worry, we're going to do more examples. Now let's take a look at this one. So this is nothing but y equals negative x to the fourth. Okay, so again, it's a negative and an eventh power, so our end behavior of the graph is both pointing downwards. So now let's try to express where this tail end is going in terms of a limit. All right, so let's take a look. Now this is telling us that, look at, when x is going towards negative infinity, right? As x goes towards negative infinity, where is the tail end of the graph going? It's going to keep going and down and down and down, so it's going to go to negative infinity, doesn't it? So we would write this as f of x approaches to negative infinity as x goes to negative infinity. Does that make sense? So let's go through it one more time, okay? So our x value is going to keep going towards the left-hand side, which will be at negative infinity. It's going towards negative infinity. Now let's look at the corresponding y values, right? So the corresponding y values as x travel towards negative infinity, look at it. This tail end is going to keep going downwards, so it's going to go to negative infinity. So that's how you would write it. Our y value, which is f of x, is going to go to negative infinity as x goes to negative infinity. All right. Okay, so now let's take a look at this end. Okay, so let's think about it. So in this case, I'm traveling x towards the positive infinity now. All right, now as x goes to positive infinity, where is this tail end heading to? What's the y value? Well, this y value is going towards negative infinity as well when x is traveling towards positive infinity. So we would write this as, where can I write it? So we'll write it right here. F of x is going to negative infinity as x goes to positive infinity in this case. Now, in a limit notation, the calculus proper way to write this is this. Limit as x goes to negative infinity of f of x. Our f of x is negative x to the fourth. Now, this is going to negative infinity. So this is where the f of x is going. And then obviously this is where the x is going. And this is nothing but your given function. All right. Now, let's try to express the other tail end. So here we're going to write it as limit as x goes to infinity of our function is negative x to the fourth. Now, where is our y value going, or f of x going? Well, it's going to go towards negative infinity. And that's how you write it. All right, how you all doing? I know this is so much information, and then all of a sudden you have this limb and then infinity signs everywhere, but you can do it. All right, so now let's look at some other function. All right, now let's look at y equals x cubed. So what we're going to do now is we want to determine the tail end behavior of this graph in terms of a limit notation. Okay, so if you want to pause the video and try to see if you can do this or not, go for it. I don't know why I'm pausing. Okay, so I'm going to pretend that you paused the video and let's go through this. All right, so let's first describe this tail end of the behavior in terms of a limit. Now, okay, ready? So this is same thing as x is going towards positive infinity, right? Where is the tail end of the graph going? Well, it's going towards positive infinity. So here, I would write it as f of x goes to positive infinity as x goes to infinity. So one more time, notice that as x gets bigger and bigger and bigger, this tail end is going to keep going up and up and up and up and up. So your y value is going to be positive infinity. All right, now let's take a look at the bottom tail end of the graph. All right, so again, you can pause the video and try to write this in terms of a limit notation. And again, why in the heck am I pausing? All right, so ready? So let's talk about this one. So this is same thing as x goes towards negative infinity. Where's the tail end of the graph going? Well, isn't it going towards negative infinity as x goes towards negative infinity? So I would write this as f of x goes towards negative infinity as x travels to negative infinity. All right. Now, to express this in a formal limit notation, we would write this as the limit as x goes to infinity of our f of x, which is x cubed. This is all going to go to infinity. Again, this infinity at the end is nothing but where the f of x is going to. All right. Now let's express the bottom tail end of the graph by using the proper notation. So this is the limit as x goes to negative infinity of our function f of x, which is x cubed. Now this is going to go to negative infinity. All right, so that's how you write it. Hopefully you're kind of getting used to it. So let's do one more. So here's the graph of y equals negative x cubed. All right, now what we want to do is we want to describe the tail end behavior of this graph. So I really want you to pause the video and try this. Okay, so I'm going to pretend that you paused it. So let's first go with the tail end behavior to describe this point. All right, so then let's analyze this again. So this is, where's my x going? Well, x is going towards negative infinity. And then where's my y value going? going towards the positive infinity. So here I would write it as f of x goes to positive infinity as x goes to negative infinity. So far so good? All right, now let's try to describe the tail end of this end right here. Okay, so now what are we talking about? We're talking about as x gets bigger and bigger, meaning as x goes to infinity, where is my y value going? Y value is going to be headed down to negative infinity, right? So I would write this as, where in the heck can I? I'll just write it right here. F of x is going to go towards negative infinity as x goes to positive infinity. All right, so let's write this out in a proper limit notation. So this, I can write it as the limit as x goes to negative infinity of f of x, which is negative x cubed. This is going to go to positive infinity. And for the bottom tail end, I can write that as a limit as x goes to infinity of our function f of x, which is negative x cubed. Now this guy is going to go towards negative infinity. How you all doing up to here? Again, I know this is so much new information, like pounded in your head, but now I think we can use all the tools that we just learned to sketch almost the perfect graph. Okay, so what I'm going to do now is I'm just going to make a summary so that way we don't forget what we just learned in this crazy section. So let's go with Dr. Knox's summary of the graph of a polynomial function. So suppose your f of x looks like that. an x to the n plus all the way up to a sub 0. First, the degree of f of x in this case is n, because n will be the biggest, and the leading coefficient is a sub n. Next, the y-intercept can be found as set x equals to 0 and then solve for y. So that's same thing as computing f of 0, but if the polynomial function look like this, if I plug it in 0, then only survivor will be the constant term, which is a sub 0. Number 3, when you graph the polynomial function, your graph better be smooth and continuous. There is no discontinuity, or there are no kinks or anything like that, or sharp edges. Number 4, maximum number of turning points. Now, if the degree is n, then you're going to have at most one less many, right? So you're going to have, if the degree is n, then the maximum number of turning points that you're going to have is n minus 1. Number 5, at a 0 of even multiplicity. Do you remember what's going to happen? Graphically, the graph of f just going to touches the x-axis. It's not going to cross. So there is that. And number 6, at a 0 of odd multiplicity. Now we talked about that then. The graph crosses the x-axis. Number 7, between the two consecutive zeros, the graph of f is either above or below the x-axis. Now, the end behavior. So remember, for a large value of x, the graph of f is going to behave just like the graph of the power function with the highest degree. So in this case, let me just write that out. I'm going to write it as for large x, the graph of f behaves like the graph of y equals a sub n x to the n. And number 9, remember that we analyzed what's going to happen to our power function if n is even or odd, and then if your leading coefficient a sub n is positive or negative. So let's first go with if a is positive and then n is even. So think of y equals x squared. The tail end is going to go this way. Next, if a is negative and n is even, then the tail end of the graph is going to go the other way around, which is both are facing downward. Think of it as y equals negative x squared or something like that. Next, if a is positive and n is odd, tail end of the graph is going to go, remember the disco motion, Left hand side is going to go down, right hand side is going to go up. Lastly, if a is negative and then n is odd, it's going to behave the other way around. So you're going to have up and then facing downward. And I think this is a pretty good summary. I don't want to add any more. All right, so the last thing, let's write down all the steps how we can analyze the graph of a polynomial function and how to graph it out. Step 1, find the end behavior of the graph. Step 2, find the x and y-intercepts. Step 3, find the zeros of f and their multiplicity. Now remember, if it's even, it touches. If it's odd, it's going to cross. Step 4, find the maximum number of turning points. And finally, step 5, use 1 through 4 to draw a complete graph of f. And if you need an additional point to graph it out completely, feel free to do that. Yes, I think we are ready to do some concrete examples on how to graph a polynomial function completely. The moment that we have been waiting for. So let's take a look at example 6. Analyze a polynomial function f of x equals 2x plus 1 times x minus 3 whole quantity squared by following steps 1 through 5 that we just talked about. Step 1, find the end behavior. So in order for us to do this, let's just expand f of x by multiplying everything out. So our f of x is going to be 2x plus 1. And then x minus 3 whole quantity squared means we're going to have a x minus 3 multiplying here by x minus 3. As you can tell, that our leading coefficient is going to be 2x to the third, because if I multiply this first term together, then you're going to have 2x squared, and then eventually you're going to be multiplying 2x squared with this x, so you're going to have 2x cubed. So your power function is going to become y equals 2x cubed. But anyways, let's just do this formally. So here, let me just multiply the first two together, which is, I'm just going to work on these two. So we're going to have 2x squared and then minus 6x plus x and then minus 3, and then we're going to multiply that by x minus 3. Let's just simplify this. We got 2x squared and then you're going to have minus 5x minus 3. Now we multiply that by x minus 3. Okay, so then 2x cubed and then minus 6x squared and then minus 5x squared and then plus 15x minus 3x and then plus 9. All I did was I just multiplied the trinomial multiplying by the binomial. Okay, now let's combine the like terms. So we got 2x cubed. Now let me see, x squared, is that all only the x squares that we see? Yeah, so that's minus 11x squared. And then what do we got? 15x and then minus 3x. So that's going to give us plus 12x. And then the constant term is just going to be plus 9. So this is our f of x, which is same thing as the polynomial function given above. But anyway, so let's keep going. So f of x is going to behave just like our power function y equals 2x cubed. All right, so now let's just draw out what the tail end of is going to look like. So we have the odd power and the coefficients positive. So that means that we're going to have the disco motion going this way. That is going to be the tail end of our graph. All right, now let's go with step 2. Find the x and y-intercepts. So let's go with the x-intercept first. So to find the x-intercept, what do? We're going to set y equals to 0, and then we're going to solve for x. All right, so then what I'm going to do is I'm going to use our original function f of x. To me, that's easier for me to solve for x. So let me do that. So what I'm going to do is I'm going to set our f of x, which is 2x plus 1, x minus 3 squared equals to 0. Well, that means that either 2x plus 1 is 0 or x minus 3 has to be 0. So that implies that we're going to have 2x equals to negative 1, which means that x is negative 1/2. And then other one's easy. So this is going to be x equals to 3. So our x-intercept are going to be negative 1/2 comma 0 and 3 comma 0. So that's the point that we're going to be plotting when we graph it. So let me just box that. All right, so that's our x-intercept. Now let's go with the y-intercept. So how do you do it? You're gonna set x equals to 0 and you're gonna have to solve for y. Okay, so you can pick and choose whichever function that you want, whichever meaning the original one or this one, the expanded form. But if I'm gonna set x equals to 0 and solve for y, right? Isn't it much easier to take this function right here? Because this is already of the form y equals 2x cubed minus 11x squared plus 12x and then plus 9. So when x is 0, then your leftover is just 9. Okay, so that's going to be our y-intercept. All right, so let me just do that. So if I have to show all the work, then I'm going to get y equals 2 times 0 cubed minus 11 times 0 squared plus 12 times 0 plus 9. So that implies that our y-intercept is going to be 9. So for sure, we're going to be plotting 0, 9 on the graph. So I'm going to box that as well. Moving on to step 3, find the zeros and multiplicity. So when I want to find the zeros and multiplicity, I will take our original function, which was defined by, let me just rewrite it, f of x equals 2x plus 1, and then x minus 3 squared. We already know the zeros. Zeros, remember, they're exactly the same thing as x-intercepts. So let me just write it as the zeros, maybe I should say. So when x is negative 1/2, we have the multiplicity of 1. Okay, so do you remember what the graph's going to do? If the multiplicity is 1, yes, it is going to cut across the x-axis. All right, and then let's go with when x equals to 3, that's another 0, then we're going to have a multiplicity of 2. So that means that at x equals to 3, your graph is going to touch x equals to 3. It's not going to cross. So let me write that out. So this means that your graph's going to cross at x equals negative 1/2, and it's going to touch at x equals to 3. Step 4 was find the maximum number of turning points. All right, so what do you think? Well, isn't our f of x, is the degree of that is 3, isn't it? So our degree of f of x equals to 3. So the number of turning point is at most 3 minus 1 many, which is going to be 2. Okay, so let me just write that. So the maximum number of turning points, it's going to be 3 minus 1, so which is going to be 2. And finally, step 5, use steps 1 through 4 to graph. Now, before I do the precise graph, right, I like to make a little, like a little sketch before I actually do the precise graph. So let me just do that. Let's just gather all the information and just determine what the graph is kind of like going to look like. All right, so this is x and a y. Okay, so the end behavior of the graph went this way. Right, remember it was a disco motion. And then let's just jot down our x-intercept. X-intercept was at negative 1/2, and then one of them was at 3. Now the y-intercept was 9. So again, this is completely drawn off the scale because I'm going to call this value 9. Okay, so now let's think about it. At x equals to negative 1/2, we had a multiplicity of 1. So that means that our graph better cross the x-axis at x equals to negative 1/2. So our graph's going to cut across this way, no matter what. And the tail end of the behavior is facing downward. All right, and then let me just go with x equals to 3 with a multiplicity of 2. So that's going to have to touch the our x-axis at x equals to 3. Now, since let's not forget our precious y-intercept. So I know for sure this is completely ugly looking graph. It has to go through 9 because that's our y-intercept. So you need to come down, and then it has to touch x equals to 3. It cannot cut across. And then look at the tail end behavior. Tail end behavior is going upward. So from here, it's going to go upward. All right, so this will be my little ugly rough sketch. All right, so now let's try to graph this out nicely. All right, so let's do this. So step number 1, I'm going to first of all, please notice that the grid is not evenly scaled out. All right, so I want you to notice that first. So that means that this will be 1, and this will be 3, and then this part will be 10. Okay, so keep that in mind. So this will be negative 10, and then you see negative 20. So this is negative 1 and negative 3. All right, but anyways, let me just jot down the x-intercept or the 0. So it's negative 1/2. So that will be here. Please label your point at all times. So this point right here is negative 1/2. Oh, sorry, that was a comma 0. And then another x-intercept or the 0 is at x equals to 3. So this will be, let me write it here, 3 comma 0. And we have the y-intercept at 9. So maybe 9 will be right here. Okay, so let me just call that point 0 comma 9. Okay, now look at the little sketch that we did. So yes, we can connect those dots and whatnot, but let's if I want to do the little precise graph, right, let's see what's going to happen when what the y value is going to be when x is maybe negative 1. So what I'm doing is this. Okay, great. So yes, I know that my graph's going to go like this way, but then where am I when x equals to negative 1? Am I like up here? Am I closer here? Am I going to be closer to more like the y-axis, right? So let me just figure that out. So I'm going to compute f of negative 1, just an extra point. Okay, so then if I do that, then I'm going to have 2 times negative 1 plus 1. And then here you're going to have negative 1 minus 3 squared. All I did was just to plug the negative 1 into our given function here. All right, so then what do we get? So this is the same thing as negative 2 plus 1, and then negative 4 squared. So this is going to be negative 1 times the negative 4 whole quantity squared is 16. So this will be negative 16. So for sure, the graph is going to go through when x is negative 1. Your y value is going to be negative 16. So that's an extra point that we can plot. So maybe that will be negative 1 and then negative 16. So that's 15, like maybe right here. All right, so that was the negative 1, negative 16. Okay, so I think we're good to go. So ready? So let's just connect. Oh dear Lord. Here's my y-intercept, and then it's going to dip down, and then it's going to plop back up. And if you want to get more precise points, right, maybe you can go like this. When x is 1, what is going to be my corresponding y value? Okay, so am I going to go dip down this way, or am I going to go above? So I have a feeling we're going to go above here, not directly down. Let's just do it. So here, right, let me just compute what's going to happen at f of 1. Then you're going to have 2 times 1 plus 1, and then 1 minus 3 squared. So this is going to be, you're going to have 2 plus 1, that's, what is that, 3? Is that right? 3, and then you're going to have a negative 2 squared. So you're going to have 3 times 4, which is 12. So here we're going to go through 1 comma 12. So as I guess, it's going to go above the 10 when x is 1. So let me try to redo this. So my redo, I'm going to draw that in purple. Okay, so far so good. And then this point, what we just discovered is when x is 1, we're going to have 12. So it's going to be over here. So this will be like maybe right here. So our actual graph, most likely it's going to go this way. It's going to go straight up, and then it's going to keep going up, then touching x equals to 3. And then if you want to know how far the graph's going to go from here, right, if you really want to do the precise graph, maybe you can compute where that graph is going to go when x equals to 4. Hey, we're here now. Let's just do it for heck of it. Okay, so when x is 4, what do we get? We're going to have 2 times 4 plus 1, multiplying here by 4 minus 3 squared. So that's same thing as, what is that? 2 times 4, 8. 8 plus 1 is 9. And then 1 squared is just 1. So here you're going to have 4 comma 9. All right, maybe I should be boxing this. Let me just box that. So these are all the additional points that we're going to plot. All right, so we got 4 comma 9. So where is it? We have a 4, and it's going to go to 9. Kind of close, but oh well. So 4 comma 9 will be right here. So it looks like our graph's going to look more like this. I think that's pretty good. Okay, so I'm going to take our purple graph as f of x equals 2x plus 1, and then x minus 3 whole quantity squared. Yay, we did it! We're able to graph a polynomial function beautifully. This is pretty close to our actual graph of our f of x. Again, this is drawn off the scale. So if you want me to graph that out on a graphing calculator, or maybe you can graph it on your graphing calculator to see what the actual graph is going to look like on the squared screen. So here's the actual graph if the grids are equally spaced out. So as you can see, it looks like we graphed it beautifully by hand. So what do you think? Do you want to do another one? I'm pretty sure you're pretty burnt out. But let's just do one more so that we can get a good practice. I promise this will be the last example. Example 7, analyze a polynomial function f of x equals x squared times x minus 3 times x plus 4. So again, we're going to follow step 1 through 5. Step 1, find the end behavior. So here, as you can already see, that if I multiply everything out, then if I multiply x squared with x, that's x cubed. And then I got an x cubed multiplying by another x, so that's going to be x to the 4th. So our power function is going to look like y equals x to the 4th. But anyways, let me just multiply everything out. So our f of x is going to be x squared. Let me just write this part out. X plus 4. So you know what, let me just leave the x squared, and then let me just multiply these guys. Make sure you have a parentheses around that. You're going to have an x squared, and you're going to have a plus 4x minus 3x, and then minus 12. So that's x squared, and you have x squared, negative 4 plus, minus 3 is plus x, and then minus 12. Distribute x to the 4th plus x cubed minus 12x squared. So this is also our function f of x. So, and behavior. So we have let me just write it. F of x is going to behave just like, sorry, that's supposed to be a little curly equal sign, it's going to resemble y equals x to the fourth. Okay, so in this case, it's an even power and the leading coefficient is positive 1. So the end behavior is going to end up being like that. All right, now let's go with step 2. Find the x and the y-intercept. So again, let's go with the x-intercept. How do you find it? You're going to have to set y equals to 0 and then just solve for x. Okay, so it's a lot easier for me to take the original function. So let me just take the original function, x squared, x minus 3, and then x plus 4 equals to 0. So that implies that x squared has to be 0. X minus 3 is 0. And then x plus 4 has to be 0. So this one's easy. This one's x must equal to 0. X equals to 3. And then x equals to negative 4. So these are our zeros, or the x-intercept. So for sure, we're going to be plotting 0, 0, and then 3, 0, and then negative 4, 0. All right, so let me just box that because this is a very important information in graphing. Now let's go with the y-intercept. So the y-intercept, you're going to have to set x equals to 0, and then you solve for y. So for this one, right, I would take the expanded form. Well, this is equivalently easy, I guess, because look, you can take this one if you want. So if I set x equals to 0, you're going to have 0 to the fourth plus 0 cubed minus 12 times 0 squared. So do you see that our y-intercept is going to be 0? But anyways, let me just write f of 0 is 0 to the fourth plus 0 cubed minus 12 times 0 squared, which is 0. So our y-intercept is going to be at the origin. Moving on to step 3, find the zeros and its multiplicity. So let me just rewrite the original function. Our f of x equals, was it x squared, x minus 3, and then x plus 4. All right, so we have the zeros of when x equals to 0 has multiplicity of 2. So that means that your graph is going to touch at x equals to 0. All right, now the next 0 is x equals to 3 with the multiplicity of 1. So that means that your graph is going to cross at x equals to 3. And then at x equals to negative 4, that one has a multiplicity of 1. So again, our graph is going to cross at x equals to negative 4. And step 4, we need to find the maximum number of turning points. Now remember that our function f of x resembled our power function y equals x to the fourth, right? So that implies that the maximum number of turning points, it's going to be 4 minus 1, which is going to be 3. So that will be the maximum number of turning points. All right, now step 5, graph. Okay, so let's give us a little rough sketch here. So here it is. Again, this is just a rough sketch. Let's jot down the our x-intercept. So that's same thing as the 0. So for sure we're gonna have 0, 0. And then let's see, 3, 0. Let's just pretend that's 3. And then negative 4, 0. So let's pretend that's negative 4. Now the end behavior, we determined that it's gonna be this way, right? Going upward. And our y-intercept is also at a 0, 0. So this is all the information that we get. Now let's take a look at the multiplicity. All right, so it says when x is 0, we have a multiplicity of 2. So it's going to touch the x-axis at x equals to 0. It's not going to cross. So, but I'm not sure if it's going to, you know, touch here going up. I have no idea. So it's either going this way or that way. But when x is -4, right, we had a multiplicity of 1, so it's going to have to cross at x equals to -4. So let me just do that real quick. It's going to cross at a -4, right, and then tail end is going this way. So that means that at a x equals to 0, it's going to have to touch that x equals to 0 from the bottom, right? So we're probably going to have like this situation going on. All right, and then also at x equals to 3, it's going to cross, so it's going to have to go up this way, and then the tail end of the graph is going to go that way. So that's my guess. Okay, so let's graph this out. Okay, so here's our graphing paper, and this is, of course, it's not symmetrical, as you can see, because look at it, this means x is 1, 2, 3, 4, and a 5, and same thing on this side, you're going to have a negative, but here you're going to have a 10, 20, 30, 40, and same thing, this is all going to be -10, -20, 30, -40. All right, so again, this is completely drawn off the scale, and I had to do this because you'll see why in a minute. Okay, so let me just go with the our zeros or x-intercepts. So we have at 0, 0, and then 3, 0, and then -4, 0. And then our y-intercept is also at 0, 0. Now let's see what's going to happen, because I don't know how far down I need to go. So in order to determine that, you can just go, oh, sorry, this is -4, sorry about that. All right, so you can just maybe pick when x equals to -2, then what is going to be our corresponding y value. Okay, so if you want to do that, just work it as a side work. You're going to get f of -2. All right, so then this portion is going to become -2 squared, and then -2 minus 3, and then -2 plus 4. So that's going to be 4 times -5, and then times by 2. So this is going to be, what is that? -40. So here, when x is -2, our y is going to be -40. So I'm just going to plot that. What if when x equals to -1? All right, so let's see. F of -1. So we got -1 squared, -1 minus 3, and -1 plus 4. So here you're going to have just a 1. I'm not going to write that. Then here you're going to have a -4, and then multiplying here by 3, so it looks like -12. So you got -1 comma -12. All right, now let's see, just for fun of it, let's just say what's going to happen at f of -3. So then what do we get? -3 squared, and then -3 minus 3, and -3 plus 4. So this is going to be 9 times -6, and then multiplying here by 1. So that's -54. Oh, so we're gonna have -3 comma -54. Okay, so let me just box all that so we have a pretty good approximation of how the graph is gonna go. Okay, so we have -2, and then comma -40. So for sure it's gonna go through this point here. So let me just jot that out. So this point here is -2, -40. All right, and then when x is, let's go with -3, then let me see, where is my x equals when x is negative 3, it's going to go to negative 54. So it's going to dip down here. All right, so then let me just draw that out. Where am I? Negative 3, and then are we here? Like maybe right here? I think that's pretty good. All right, so then let's go on the positive x-axis side, right? So far so good, because we have this situation going on. So we're gonna have this going on. And it looks like it's gonna go this way, right? And then, oh, when x equals to negative 1, it's gonna go to negative 12. So it's gonna have to go through like around here somewhere. So it's gonna have to go through here, and it's going to touch. All right. So far so good. Now let's just analyze the positive side. So in order to do that, you can just compute like maybe f of 1. So f of 1 is going to be 1 squared, and then 1 minus 3, and then 1 plus 4. So that's same thing as negative 2 times by 5. So that's negative 10. So you got 1 comma negative 10 to plot. So let's go. 1 comma negative 10, so that will be here. Okay, so now let's see. Let's compute what's going to happen at x equals to 2, because look at it. I already know that at x equals to 3, it's going to have to cut across, right? So what I'm trying to do is how far down do I need to go before I plot back up and then go through x equals to 3. So that's the reason why I'm going to compute f of 2. All right, we got this. F of 2 is 2 squared, and then 2 minus 3, and then 2 plus 4. So this is going to be 4 times negative 1 times 6. Is that right? So that's going to be negative 24. So it looks like I need to plot 2 comma negative 24. Now, if you want to find out how far this tailend is going to go when x is 4, then just compute f of 4. So we have f of 4 equals 4 squared times 4 minus 3. And then we're going to have a 4 plus 4, right? So let's just, what the heck, let's just do this. We're going to have, so this is going to be 16 times by 1, and then times by 8, which is, what the heck is that, 128? Oh, that's going to shoot up really high up there. So we're going to have, when x is 4, y is 128. So I don't even think we can plot that. So basically what's going to happen is when x is 4, we're going to be way up in here. Okay, so let me just pretend that this is 4 comma 128. All right, so I think we're good. So we're just going to go like this. Phew. Oh my gosh, pretend that's, smooth. Okay, so I'm not going to mess with this anymore. Okay, so I think this is a pretty darn good looking graph. Now, if you wanted to graph this out on the graphing calculator just to see what's it look like exactly, go for it. So this is the actual graph. I'm ran out of room here. It didn't print out, sorry. So it's gonna go something along this line. All right, so I think we did pretty good. Okay, so I am officially done. I cannot do anything anymore for this section. We have learned so much in this section, and at first all the limit notation is going to be all confusing and whatnot. But anyways, if you have any questions at all, please let me know. Okay, but anyways, great job everyone, and I'll talk to you soon.